So in a couple of previous videos, Chris has explained the relationship of voltage and current in a delta and in a Y transformer. There's a couple of general things that we haven't discussed yet that I think would be important to go over real quick. Transformer is not a power source. Therefore, power in is going to be equal to power out. Generally speaking, there is a efficiency of transformers that can be taken into account, but in general terms, power in will be equal to power out. We're going to assume a 100% efficiency. The other thing I think would be good for us to discuss is the quick identification of a Y or delta transformer based on the voltages and the slash ratings. Again, real fast, if I had a 277, 480 volt transformer, if I take the lower of the slash rating, 277, and I can multiply it by the square root of 3, which is equal to 1.732, I'm going to get 480 volts. Okay, I know that I have a Y transformer if that's what I have to do. Conversely, if I had a 240, 480, these numbers are directly divisible by 2. And I know that I have a delta transformer. And this would be my Y. So what I'd like to do is bring it all together, do a quick calculation. I'll switch over to the slides, and I would like to show you how this all works together. I'll do a quick calculation from a Y to a delta, and then back to a Y transformer again, and we will discuss the voltage and current relationship that they will have with one another. All right, and here we are, through the magic of television, inside of a PowerPoint. So what we're going to do is we're going to put all this together. We're going to do some examples of calculating coil voltage and currents in a Y and delta, like we discussed. This is our setup. We have three single-phase transformers that have been connected to form a Y delta bank. The primary is connected to a three-phase line of 13,800 volts and the secondary voltage of 480. A three-phase resistive load with an impedance of 2.77 ohms per phase is connected to the secondary of the transformer. If I were to draw it out, this is what it looks like. Everything we discussed, 13.8 primary going to a 480 volt with a Y-connected load of 2.77 ohms. Given the information that Chris has given us in the previous videos, we can solve everything here, with the exception of maybe the turns ratio, which we can cover real quick. So it looks complicated, but I want to show you how incredibly easy this is. The first thing we would do is we would say the primary windings of the three single-phase transformers have been connected to form a Y. In a Y, the coil voltage is less than the line voltage by a factor of the square root of 3, or 1.732. Therefore, all the coil value of the primary voltage is easily calculated. Coil divided by 1.732. So I automatically know that my coil voltage is going to be 7,967.667 volts. Very simple math. The secondary windings are connected as a delta, and in a delta, we know the coil voltage and the line voltage are the same. This will also be the line voltage applied to the load. So we already know now that we have voltage in the line and voltage in the load at 480 volts. The turns ratio, this is the one thing we did not discuss. The turns ratio can be calculated by comparing the coil voltage in the primary with the coil voltage in the secondary. And since we now know the coil voltage in both, we see that we have a 16.6 to 1 turns ratio. I'd like to also point out we are saying coil voltage. In all previous videos we've said phase voltage, so wrong or right. I just want to point out that we are using those terms interchangeably. Wrong or right, we're doing it that way. So we now know we have a primary and a secondary turns ratio of 16.6 to 1. We know most of our voltages already, and we've done very little. This is just so easy. So the load bank is connected in a Y connection. The voltage across the phase of the load bank will be less than the line voltage by a factor of 1.732. So again, it's the same math, only in reverse for a delta. The voltage for phase at the load is going to be the voltage from the delta secondary, 480, divided by the square root of 3, which is 1.732. So we now know we have 277.136 volts. So we know we have a 277 480 volt Y with a 2.77 ohm three-phase load. Now we have voltage across the loads. Each of the load resistors is known. The current flow through the phase of the load can be calculated using Ohm's law. We have 277.136 volts and 2.77 ohms. We have 100.049 amps. So now we have the amperage as well. So because the load is connected as a Y connection, the line current is the same as the phase current. Look at that. Power in is the same as power out, 100.049 amps. The secondary of the transformer bank is connected as a delta. The coil current of the delta is less than the line current by a factor of 1.732. So we have 100.049 for the line current, and the coil current divided by 1.732. We end up with 57.765 amps in the coil. Not a lot left for us to do here. We could again look at our turn ratio. The amount of current flow through the primary can be calculated using the turns ratio. Because the primary has a higher volt than the secondary, it will be a lower current. Again, power in is equal to power out. So secondary current divided by the turns ratio, 57.765 amps divided by the turns ratio of 16.6, we end up with 3.48 amps. All right. Because all the transformer values of the voltage and current take place across the phases, the primary has a phase current of 3.48 amps in a Y connection, and the coil is the same as the line current. So now we could see we brought it all together. We could do all this math individually. This one sheet should show you everything that you would need to know. You could see what's that my voltage on my line versus my phase in a Y is different by a factor of 1.732. My current in a delta is different by a factor of 1.732. It's really pretty simple. If it's the first time you've ran across this or you're trying to do this calculation, it may seem complex. I just really wanted to show you how easy it can be. Thank you for watching, and if you like what you see, please like and subscribe.